Okay, people, today we are going to be doing ratio lemma. Now, ratio lemma is a pretty niche topic in Olympiad geometry, but we still use it. Why? Because of its interconvertibility. Yeah. Okay, so first of all, let's just go through the entire theory. It's really not that much. So these are the notations we'll use. Fix 2 points BC. Our entire setup will be based on these 2 points. Okay. And then like we define FP to be a ratio between the distances from BC of P, and we like have some sign convention. This is important. We'll see why this is so important later on. So for illustrations, here we take the positive direction to be above towards A. So f of A is equal to plus AB by AC. So and now the main ratio lemma. Ratio lemma is like just a basic statement. It's just sign rule. Like trust me, it's not that deep. And then this is the like, yeah. Now this is the cool ratio lemma. This is the important things will, and this is the only thing we'll use. Wait, let me like how to draw. Okay, nice. So suppose we have a circle BC, and like BC lies on this circle. Let A be any random point. Let D be any random point. Basically, the point is when we connect A and D and let the intersection be something like E, we have the powerful result F A. Also, like ignore my handwriting. It's very quick. I never use like one note or stuff. Into FD is equal to FE. The proof of this is like, very trivial. Like I posted this, and now like the proof is actually pretty easy. This is also the place where we like use a bit of sign convention, because since this is positive, this is clearly negative. So positive times negative is negative. So this will be negative. It's like checks out here. Like you might also have noticed that obviously it would also hold if everything was positive. However, the reason why we don't have stuff positive is because like consider these 2 points A and D. The point is, what if we are given f of A is equal to f of D without the sign convention? Can anyone like remove the annotations? How do we remove the annotations? Okay, nice. F of D. What can we say about A and D? Are these the same points? Like, can anyone speak up?
Usually
Okay, I use
trying to characterize points
what?
based on what their function, the value of the function is in the sense that in this case, even f of A is equal to f of D. A is not D, right? A is the opposite.
A, yes, exactly.
That helps.
A can. There are cases where A is not D. Okay, so someone is asking in the chat what is f of A. F of A is basically uh, like consider these 2 points B, C. Consider any point, like it can be some random point here. Connect these 2 points, these two distances. Then the FA is given as AB over AC. This is taken to be positive whenever A is above the line A, above the line BC, and otherwise negative. So if A lies somewhere here, then the ratio will be negative. And if A lies here, then the ratio will also be negative. Now this sign convention we use because it helps us tell when 2 points are at the same point. We'll see this later on too. So consider this point AB by AC. There exists another point. Like, wait, is this the median point, right? Consider the intersection of these two tangents and like draw this. Call this point A dash. Then what do we know about f like A dash? What is A dash? Anyone? Also, it's like hard for me to keep checking chat. So, but like you could send messages on chat. Okay.
Yeah, so they're negative for each other.
Yeah, this is exactly the negative of minus f of A. Nice. What if we did not have the sign convention? Then this would also correspond to f of A, and then we would not be able to tell if this is the point A we are looking for or not. Also, like, trust me on this, but as we vary A here, because of continuity, everything will be different. So, like, basically, the thing is, if f of A is equal to f of x, where uh, A and x both lie on a circle going through B, then A is equal to x. So, like, consider any random circle omega and consider B and C. Consider any random point A and another point x. It is not possible that AB by AC is equal to BX by XC along this arc, which is why we are using the positive convention for these to be equal. Just like for a visual proof, just notice that as we move A to X, the length AB increases and length AC decreases. So the net ratio always decreases. But this is like very not so important stuff. Just remember this. Okay, so does the class feel too fast? By the way, anyone? Wait, please speak up. Like,
But what were you saying?
like, does the class feel too fast paced?
No,
No, no, it's fine. It's good.
Nice. Does anyone know what the butterfly theorem states? I forgot.
No,
Okay, never mind. This is it. Okay, so the butterfly theorem the states if this is the midpoint of AB, and then we consider any two random points PQ and RS going through M, and let like PS like intersect AB at X, and let RQ intersect AB at Y. then M is also the midpoint of XY. Like, just try this problem for a few seconds. Like, just get the grasp of this problem and like try to do it with the ratio lemma, obviously. The main thing to note is these 3 points are very well related. Like f of this and f of this multiply out to f of this. Just try to use this. This is like doable with this. Okay, so any ideas? Like type them in chat if you feel like it.
So Fp times Fq is 1 and Fr times Fs is 1.
Yes, like, nice. That's the idea. So basically, in these types of problem, what we try to do is first we fix a line AB, like fix a line BC. So here, but the only obvious candidate of this like looks AB. I think everyone agrees with me on this, right?
Yes.
Nice. Then what we do is try to compute the ratio, like the value of f in terms of other f's which are easily obtainable in this problem. So for example, m is easily obtainable because f of m, oh my god, my handwriting is crooked too. F of m is equal to minus 1 minus ma over mb. Now, does this like seem familiar? Because MA and MB are equal. Since M is the midpoint of AB, then we have this is actually equal to minus 1. So nice. We have one of the points. How many points do we need to calculate? Okay, so we have A, we have B, we have M. But can we calculate P? We cannot like point is the main motivation is we cannot actually calculate P. This is due to the fact that this is a variable chord. Like it just has to pass through M. Anything could happen to it. Like we don't actually know the ratio of P. Wait one second.
I'm sorry, I just joined. What is going on right now?
Okay. Hello Aswat. Okay, so we are just doing ratio lemma. Till now we have just defined ratio lemma. Do you know what ratio lemma is? Or like should I define it again?
Uh, uh, yes, please. Oh, yeah. Wait. Yeah, yes, please. That would be that's nice.
Nice. Okay. Till then people can just try butterfly theorem. Uh, okay, so like FP is very like easily defined. Just see this slide. If A is above line BC in the positive direction, then f of A is equal to plus AB by AC. Otherwise, it's negative. Like if it is here, then this plus sign will change into negative. And if it's on the line BC, then it's also negative. Then we have this span thing. I don't know. Like this is just trigonometry, sine rule. And then we have this, the main theorem in all its glory. So basically, by sine rule, it's not that hard to like find. Like suppose we fix line BC and like we define the ratio function. This is B, this is C. If we take any other point A, then we intersect it with another point D. Then the main point of this entire lemma, which is like the only theorem we'll be using, like mostly, is f of A times f of D is equal to f of x. Is that clear?
Yeah. Thank you.
Nice. Okay. Then we will trying this butterfly theorem, which I'll explain the solution to now with motivation. Okay, so we have already calculated f of m. This was minus ma by mb, but ma and mb are just the same thing because m is the midpoint. So we have minus it equal to minus 1. Now, since we can't calculate f of p directly, we'll just try to find relations. Just spam random relations. You don't really have to think about anything at this point. F of p times f of q is equal to f of m, right? This is by the theorem. Like this
Yeah.
is our first relation. Okay. And this is just equal to -1, which is pretty nice, don't you think? Like f of p, like we can define q in terms of p, but like and we do the same thing for the chord rs. Then we have f of r into f of s. Okay, cool. Now, which other points have we not found the ratio, like the ratio function of? The answer would be x and y. But notice finding x and y is also trivial because we already know p, we already know s, so we can find x in terms of p and s. So we have
ABPS quadrilateral, I think. ABPS point, I think we can use.
what?
ABPS point. Because we know
True.
AB and PS.
Yes,
Then
so
their
we can use,
intersection
yeah,
X.
yeah, exactly. Nice. So f of p times f of s is actually equal to x. Okay, similarly, actually, I think we should just ditch writing the f now. So, like, if I write f of p, I'll just use the notation p bar. Like, if at any point you get confused, just tell me. So, we have r bar into q bar is equal to y bar. Interesting. So, like, r bar times q bar is equal to y bar. This means that f of r times f of q is equal to f of y. Okay. So now we have found everything we could. Now, what do we even want to show? This is like one of the main ideas of Olympiad geometry. You want to reverse engineer things. This, in other terms, is also called forward backwards thinking. So we want mx is equal to my. What should be the relation of x and y in terms of like the ratio function? So like if mx is equal to my, then what will be the relation of x bar and y bar? Like just take your time on this. This is pretty easy to derive. Just try this like for a minute or two. I'll be right back.
X bar is equal to 1 by Y bar. I said x bar is equal to 1 by y bar.
Yes, very good. That's the answer. Because like x bar, if we try to calculate this, so x bar will be just ax by bx, y bar uh, will be just what ay by by, right? Is this clear? Because okay, now we claim that these two things are actually equal, which is just easy to see. Like come here, uh, ax should be equal to by, but now ma is equal to mb and mx is equal to my. So we subtract ma minus mx and we subtract, and this is actually equal to mb minus my. But now ma minus mx, come back here. Ma minus mx is just ax, and like the other thing is just like by. Nice. So and like the similarly, stuff just works out. So we just want to prove x bar into y bar is equal to 1, right? Like the mod value is 1. Wait, we don't even need the mod value. Like x bar into y bar is equal to 1. So we reverse engineered the problem and found that we just have to prove x bar into y bar is equal to 1. But now coming back to our relations, we just that just means we want to prove like when we multiply these two, we have x bar into y bar is equal to r bar uh, pqrs, the functions related to pqrs. But now we already know pqrs. Like what's the multiplication of pqrs? Fp into fq into fr into fs is just minus 1 times minus 1, which is just equal to 1, and hence we are done. Does everyone get this?
Yeah.
Yes.
Nice. So the main thing you should learn from this is that obviously the procedure. First we like fix a line AB, then we find f of m, then we like f of like all the points. Like, yeah. Then we use the main ratio lemma theorem. Then we just find out what is to be proven. Can we write it in terms of ratio lemma? And then we are done. Also, this technique is actually what's called a soft skill. This is like very useful in a lot of geometry problems. Like you should definitely keep this in mind the next time you try a geometry problem, which will like obviously be in this lecture. Okay, so now like just take a minute to like read through this, and then I'll explain why do we even need ratio lemma? Why don't we use some other stuff? Why don't we just angle cis? Why don't we follow the words of the dictators and like we prevent bashing? Like ratio lemma is just kind of bashing too, but like yeah. Okay, so like there are some common themes in geometry, like angle chasing. It's just angle chasing. Then we have transformational ideas, like the major of them are like spiral similarities and inversion. Then we have projective geometry, where we like also have method of moving. Don't ever use this, guys. By the way, like they will like people will tell you to use method of moving point. It like makes your life easier, but never use this. And then we have like basing. Okay, so the point of ratio lemma is that we can convert a lot of these things into ratio lemma. Angle chasing we can convert to like ratio lemma by just considering the sign of stuff. And like we already know, and we have already shown here how things of signs can be related to the ratios, to the function of the ratio. Then we have transformational ideas. Like these two are the same thing. I will teach how to deal with spiral similarities. For those who don't know what a spiral similarity is, don't worry, I'll just explain this. Inversion is also sometimes useful in ratio lemma. Like ratio lemma can be used to like not use inversion sometimes, but I don't think we'll be dealing with this in this session. I'll probably like make a piece set and like send it to you guys. You should solve that. Anyways, then we have projective ideas. First of all, look at cross ratios. Does anyone know what a cross ratio is? Anyone?
Yes.
Okay, can you like uh nice. So oh just a second.
CA by CB, DA by DB is equal to.
Right. Uh so the fact is this is just defined as CA over CB divided by DA. Okay, wait. What? So delete this. Uh, okay, so CA by CB. Wait, right. Have I written this correctly? Oh no, I have not. This is B, guys. Okay, so ABCD is just defined as CA by CB is equal to divided by DA by DB. How can anyone see how this is related to ratio lemma? It's pretty easy. Just like consider the line AB, fix the 2 points AB. Now, can anyone see the relation between cross races and ratio lemma? Oh wait, I've not been reading chat. This is crazy. So
So,
many messages.
maybe the line will be right.
I think it is ratio and point which is relevant.
F of C and F of D.
Yes, exactly. This is this f of c over f of d. So this just goes to show how much utility like ratio lemma has. Like why we even use ratio lemma? Wait, is this plus minus? Okay, just like, whatever. Okay. The reason why we use ratio lemma instead of a lot of other things is because a lot of these things are interconvertible to ratio lemma. This like gives ratio lemma a lot of utility. Sometimes you want to like use some stuff and like you're not sure of what to use. Now ratio lemma is your answer. Like ratio lemma you can use in a lot of things. Trig bass is also basically this ratio lemma. Anyways, uh, okay, now I think we should get down to like actual problems. Now that we have seen the utility of ratio lemma, the next problem I'm going to show is actually a projective problem. A lot of my friends bullied me for doing it with the ratio lemma, but like, the ratio with like the problem with the ratio lemma is very like trivial. Where's the slide? Okay, nice. So like try this problem for like 10 minutes. Like just try to understand this problem. Okay, I'll just give a hint right now. Try to convert this into ratio lemma terms. Okay, someone just joined. So basically, like we are trying this problem. We have like done the basic theory of ratio lemma, and like this is actually not a ratio lemma problem. We are trying to use other things. Like this is a projective geometry problem, but we'll not be using projective geometry for this one. And like just this just goes to show how much utility like ratio lemma has. So like, yeah, the main hint is just try to convert this into like this is a minor hint. This does not instantly solve the problem, but the main hint is just consider this and like convert it into like ratio lemma terms. If anyone is done, like they can write the idea to me on like Zoom DMs. Yeah. Also, like I can share a buffer problem too if people are done with this.
So in the problem, we are given the quadrilateral as ABCD, but in your diagram, you have drawn it as ABBC. Doesn't that matter?
It like does not matter. I've not really checked, but it should not matter.
Yeah.
Actually, yeah, you're right. Like it should be like for convenience, like it should be ABCD. It does not matter mathematically, but stylistically, I'm having lots of trouble to draw the diagram. Hold on, I'm copying on the diagram. Like I'll try to use GeoGebra for this, like to draw the diagram. Like in contest, you should like try to draw the like draw good diagrams. Like obviously, don't be like me. Like I'm just copying here. Anyways, is the picture visible?
Yeah.
Nice. Okay. So like let's just hear like complex Bassett's solution.
Yeah, sure. Okay, so how I start by AB times CD is equal to AD times BC, rearrange that into a ratio. We get AB
Okay.
upon AD is equal to BC upon CD.
AB upon AD is equal to BC upon CD, right?
Yep.
So like we have like ratio stuff.
Yeah, then in by ratio lemma and ACD, triangle ACD, we get sine of CAB upon sine of BAD is equal to sine BCA upon sine BDA.
Sure.
Right?
Or wait, actually, like let me just explain the solution. What is the like gist of your solution?
So basically just substituting all the Samidian steps with first we just prove this AB and AD are isogonal in ACD.
ACD, how are like AB and like
Uh, so I got sine CAB upon sine BAD is equal to sine BCA upon sine BDA.
I see. Okay, maybe that leads to a solution, but yeah. Okay,
Yeah.
so what do you want to prove? Like PB times ND is equal to PD times NB.
Yeah.
So like rearrange this ratio.
I
Wait,
do that at the end. That's my final step. I'll get
nice.
that in
Uh,
terms of. Okay.
well, nice. Anyways, PB by PD. So
Is
like
equal to NB
fix
upon
B
ND.
and D because like this is way more convenient. So f of wait no, like we were following some other convention. So like we are defining ratios with respect to B and D. So P bar is equal to minus N bar. This is what we have to prove. Can everyone see this? Nice. Then okay, what are we given? Let's just like let's just deal with the problem step by step. Like in contest, in geometry in general, you would like want to try to solve the problem while you are drawing the diagram. So suppose you drew the diagram of, like you want to draw C, like after drawing ABD, then you should like use Apollonius circles or Simidians or whatever to like draw C. That should give you some idea. Then you would try to like uh, gain perspective about what the line through C perpendicular to AO actually is. So uh,
That line gives us CB1A is equal to AD1C.
CB1A is equal to A
D1C.
CB1A is equal
Wait,
to
am I
AD1C.
wrong?
Yeah, I
I might be
think.
wrong here.
I think. Yeah. Okay. Anyways, but like considering the angle CB1B is the right idea. Anyways, so we want to prove. So we are given that. What's this? Like rearrange this to get A bar is equal to minus C bar. So we have to use this prove this result. So now this is a line through like the line through C perpendicular to AO. What other line is perpendicular to AO, which is like relevant to this scenario?
Uh, I have a feeling, I don't know if it's right, but
Yeah,
is
please.
O the orthocenter of AB1 D1? I don't know.
Uh,
It looks
A
like,
B1.
but I haven't proved it yet.
Wait, nice. That's actually like decent insight. That might be true, but I don't think that's really true. But like that might be worth proving because like D1, I don't think that looks perpendicular. But yeah,
Uh,
nice claim. Anyways, like what is the tangent through A? Like consider the tangent through A. Uh, what properties do we have about the tangent? The most basic one is that OA is perpendicular to the tangent, right? Like the radius is normal to the tangent at the point the radius meet the circumcircle, right? So this is 90 degrees, but we also know this is 90 degrees. So this gives us that this line is parallel to this line. Does everyone follow?
yeah.
So like how do we eliminate this condition? How do we eliminate the fact that this is a line through AO perpendicular to this is a line through C perpendicular to AO? Basically, we don't want to deal with the perpendicularity condition itself. Do we have some other thing we can use so that uh, like this condition just translates within itself? Basically, we just want to get rid of this perpendicular line. The main answer to that is just trying two angles. Is you just try out stuff. Now, what is this angle equal to? Hint alternates like alternate segment theorem. By alternate segment theorem, this is equal to this. But since this line is parallel to this line, and like these are opposite sides of the transversal and like interior angles, so we have this angle is equal to this angle. Can anyone see like interesting stuff now? Hint, just like try to find a cyclic quadrilateral in this figure.
Uh, BD1 DB1.
B D1 B D. Yeah, exactly. Now, why do we even care? Why do we even care about like some random quadrilateral being cyclic? Obviously, like that gives us some information, but the main thing is that now we can completely ignore this condition. We don't need this. Basically, we can we can define the problem in terms of uh, some random circle passing through this and blah blah blah. Basically, the point is we are not going to use this perpendicular line now, and we have a much better condition. Circles are like much better to deal with. Uh, Circles are much better to deal with than just some random perpendicular lines. We won't even need O at this point. We can delete O. We won't even need this tangent. So delete this, and we won't even need this parallel line, perpendicular line. All we do need is this circle. So now at this point, if you try the problem for a bit, you might get stuck. Actually, I'm not anyone to say that, but whatever. Uh, Point is, now we are going to again use the idea which I told you about in what was the problem? Yeah, here we motivated stuff by working backwards. First, what should be the relation between x bar and y bar? If we do this again, if we do this again, then what we have is that uh, p bar is equal to minus n bar, which is trivial. But what else do we have? We have a bar is equal to minus c bar. So we want to try to find some stuff based on this. Can anyone spot out some stuff?
So what is our new definition of B1 and D1?
Like, just ignore the definition for now. Just ignore everything. We don't even need to the definition remains the same. We just don't need to focus on O and the lines and the line through C perpendicular to AO. We just don't need to focus on those things.
Okay.
Now we can use a B and D instead of A and C.
What?
We can ignore A bar and C bar and use B bar and D bar.
Wait, no, I don't understand. Okay, so we are given these two relations. Let me just write them side by side. A bar is equal to minus C bar. Can we multiply this stuff out to conjure out some point? Also, this we have not proved yet. So assume this is true. What must also be true for this to be true? Hint, just consider multiplying these two equations out. What should we have? Also, you can type it, you can type in chat if you want.
Okay, do AP is a concurrence to BD intersect B1 D1?
AP, what? AP intersect BD.
Yes, yes.
Okay, nice. That's the idea. So if we have some intersection point, let it be X. The diagram
Then
is
we're done.
quite messy now.
Wait, don't
How are
we?
we done? Yes, Ashwat.
Then then we can multiply these two PA and PB, PA and PA, sorry, P and A, and we have N
Right.
and C. Then we get P and A in terms of X, and we also get N and C in terms of X.
Wait. Right. You're so right. This is actually the right idea. So if we multiply these two out, we'll get X bar. But if we multiply these two out, we'll get NC cap BD bar. cap just means intersect. So like we have this point. So these 2 points are the same. Nice. So what we must prove is that AP, CN, and BD are collinear. Does everyone get this?
Yes.
But don't we have that because it's a radical center for like B1D, like the
Yes.
circumcircular part, and ABD
Yes.
and like the other circle.
Yes. Exactly. That's the main like final piece. Nice. So now we are done with this. Like we are basically done with the problem. We want to prove this thing, or which is just equivalent to AP and C and BD concurring. Like, and then it's just a cookbook recipe. Like there are not many ways you can prove like three lines are concurrent. Like there are points such as like there are things such as phantom points, but one of the main ideas you should keep in mind is like radical axis. Now is the part where we use this is cyclic. Consider this circle and this circle and this circle. What does radical axis theorem give you?
That they concur there at the radical point.
Yes, exactly. So we have this, and AAP. AP, like the segment is too messed up at this point, but whatever. And AP. So nice. They concur at X, which is precisely what we needed. So we are done with the problem. One important thing to keep in mind is even though we did so much reverse engineering, we like it's better to like write it out in like in forward thinking manner in like the actual context because that might confuse the graders or something. Anyways, like it's not a necessity, but like the solution just looks clean. So what I'm trying to say is first we would prove B1 B D1 D cyclic. Then we would prove that AP and C and BD concur. Then we'll prove by ratio lemma that this happens. Which just finishes. Uh, so yeah, like we don't try to use our motivation for this. This is only for motivating stuff. This is the essence of like forwards and backwards thinking. Anyways, another thing I wanted to deal with is spiral similarity and ratio lemma. How can spiral similarity be related with the ratio lemma? Do people know what spiral similarity is?
Yeah.
What?
No, I haven't heard of it.
Okay, just ignore the complicated term. It's not really that hard. Like wait. Let me just explain spiral similarity in a gist. Wait, why am I not able to delete this stuff? Okay, so consider some point A. Consider another point B. Consider the segment AB. So, do you know what a homothety is?
Yeah.
So, suppose we have some ratio K, like it sends B to some random point C. Do you know what a rotation is? Hello?
Yeah.
So, suppose like after rotation by some angle theta, this point goes to this, like B goes to B dash. But actually, no, this is like a worse way of explaining. Anyways, okay. So suppose we rotate this. So suppose we rotate the segment AC by like subangle theta. So this goes to B dash. A spiral similarity, like uh, let it be denoted by this symbol, is dependent on three things: the center of spiral similarity, this thing, the like ratio, like the scale ratio, and the angle of like rotation. So first we like consider like dilate B, then we rotate B, which is why it's called spiral similarity. Like spiral because of the like rotation and similarity because of dilation. This is just random stuff. You don't need to worry too much about it. The main point is like, I'll use it. I'll cite it out without proof, but like just try to prove this in, like after as homework, guys. Like exercise left as an exercise to the reader. Anyways, uh, consider the intersection of this point. Consider this intersection and the intersection of the circle and this circle. By some spiral similarity stuff, you could read about it in like EGMO. Let this point be M. This point is also called the myqual point of like, yeah, this point M is called the myqual point of the complete quadrilateral E, F, A, B, C, D. Don't like stress about what a complete quadrilateral is and like what are all these complicated terms. It's really not that hard. It is just some random notation made like by mathematicians to make you scared of math. But anyways, the main point is M is like the center of spiral similarity of AB and CD. So basically, the spiral similarity centered at M, which sends A to D, also sends B to C. This is like proof left as an exercise to the reader, but the main point with this is consider triangles MBC and MAD. Do these triangles look similar? Like, first of all, these two angles are obviously the same because of spiral similarity. Then, like, by doing some other stuff too, like, you can just basically find out these two triangles are similar. What this means is M MD by MC is equal to MA by MB. Does anyone see the significance of this with respect to ratio lemma? Feel free to speak up. Like, even if you don't like, just say it.
I mean, f of m with respect to CD is f of m with respect to.
Yeah. In fact, you proved. In fact, you stated something like which is in fact harder. The main point is this is just equal to f of m. Now, this may seem very niche. Like we don't encounter m a lot. Consider like with respect to other points like altitude, medians, and like yeah. But this is actually like surprisingly many people still use m in like many problems. Many proposers like still use m. This is because it has like lots of magical properties. Like there are some handouts. I'll like probably share them after class. If you should still go through them. Those are not related to ratio lemma, but like, they build a lot of intuition in geometry. Anyways, the main point of introducing this is so that we can finally move on to the like main problems. Okay, wait, let me just pose the problem. It might have been the mod's problem, I'm not sure. Like mods has a lot of problems. Anyways, this is the problem. I will not give you guys too much time on this because the idea is pretty clear if you use like this thing. So yeah, let me just draw the diagram. This is like relatively easier to draw. Like this is A, this is B, this is C, this is I. This is the line through I perpendicular to this. Uh, yeah, nice. There's, this is the midpoint. But what other point did we have? Yeah, the interest point D. This is the point X. This is the point D. This is the point M. And like, yeah. Oh wait, I just realized some people might have done this one before. So like, if they have, then they can like request. They can like request buffer problems. Or if they have not, just tick with the list. Okay, so is everyone done with the diagram? Hello?
Yeah, yeah, that's clear.
Yeah, done with diagram.
Nice. Okay, so I'll just give you guys a hint. The point is, uh, how do you use this here? Like we have to use this. You'll eventually like if you like start using uh, complete quadrilaterals, you'll start seeing this stuff naturally. But if you have not seen a lot of complete quadrilaterals, I'll just be giving a hint. So what do we even want to prove here? AM and XD intersect at some like point on the circumcircle. So basically, if AM intersects at some point, say A dash, then like it's easy to show that A dash is just minus A, right? Like A dash bar is equal to minus A.
Right.
So now we want to show that X A dash intersects BC at D. So we want to show uh oh wait, no, this is not true actually. This is minus 1 by A bar. This is just because like these 2 points multiply are to M, but M is just minus 1. So this is what we have.
So we need to show that x bar times a dash bar is equal to bd
D.
over.
Yeah. This problem is just trig bash after some point. So yeah. So basically I'll not do the trig bash. I'll just write the equivalent statement you would have to prove, and then like you could try that as homework or something. But the main point is we want to show this is D bar is equal to this. So now like just let's just stick to the point where we calculate the ratios of some points. So we want to show this. A bar is okay. Like we know A bar, AB by AC. The problem is defined on A bar, so we don't need an explicit thing for this. So A bar is okay. D bar is interesting. So basically, in the triangle ABC, D bar is the intouch point. It's easy to calculate, say by sine rule, the ratio BD by DC. Also, I forgot to mention, but it's kind of trivial to like take BC as the reference line, but also BD by DC. Yeah, BD by DC. Right.
It, what's
This
the
is just
what do you mean by the index point?
what
What do you mean by the index point?
the interest point is like. Consider the in center I. Let D be the foot of the in center onto BC.
Okay. Yeah.
Yeah. So this is the interest point. Then like you can use this normal trigonometry to find out what BD by DC is, but I'll do it for you. This is S minus B semi perimeter. This is like the semi perimeter, and this is also S minus C. Nice. So we also know D bar. What we do not know, X bar. What is X bar? X bar is just BX by XC. But what is BX by XC? Anyone? Like just use the spiral similarity thing I told you. Consider the like complete quadrilateral BFEC,
P
and then
the
find out what is BX by XC. Oh wait, people are typing in chat.
That's just Lemma.
What?
Sorry. No, nothing. Sorry.
No, it's okay. Like, even if it's wrong, please speak up.
No, I made a mistake.
Oh,
it's equal to xf over xc. Which
yeah, XF over XC. Wait, I forgot to mention, but it is also equal to one more thing.
it's also equal to what?
One more thing, like BX by XC is equal to XF by XC. So by similarity, what it also must equal to by similarity criteria, like
Fe over bc.
uh
No,
no,
it
not FE over BC, like BF over EC, right?
doesn't.
Hello.
Okay, so that proves. Yeah.
Nice. But why does this help? This helps because we know we can define F and E in terms of ratios. So since this is 90-degree, we know AI, so we can find AF and AE, but AB and AC are known. So we can just AB minus AF is equal to BF, and AC minus CE is equal to AC minus AE is equal to EC. So basically, uh, we can find out the explicit expressions for BF and EC. Another way to do is like just do some normal geometry to find out BF by EC. This must always equal to like this must always equate to this thing.
But how is bx over xc equal to bf over ce?
Okay. This is due to the like similarity criteria. We already know that XB over XC is equal to XF over XC, right?
Yeah.
So there's a similarity sending like it's well known that there's a similarity sending BF to EC,
bf to
right?
yes, that's known.
So we know that this angle BXD
Mm,
is equal to this angle angle CEX because like they like have the same angle of rotation theta, and like yeah, is this clear?
That's clear.
So we have BF over CE is like by similarity is equal to BX over XC. Is this visible? Basically just
Yeah.
ASA criteria. No, sorry, like angle criteria. No, sorry, SAS criteria.
Yeah.
Is
It,
this visible?
the diagram's pretty much.
Okay, true. It's not visible. Basically, the point is what I'm trying to say. BXF uh, BXF is like similar to CXE. Nice. So this is the thing, right? Is this like visible to you all? Like, okay, wait, it's not. Let me just draw a better diagram. It's hard to keep track with like chat. Let me see what are people doing. Okay. Uh, this angle is equal to this angle, right? Is this clear or not? Like, I can explain again. Just say.
Yeah, it is clear.
Okay. Okay. Then like I've already like stated that XE and like XF, like XE divided by XF is equal to XB divided by XC, right? And then
Can you repeat?
like XB divided by XC is equal to
Yeah.
XE divided by XF, right?
Okay. Okay.
But these two angles are equal. So by SAS similarity criteria, we have that uh, these two triangles are similar. But then that also means that BE by CF is equal to BX by XC by like similarity proportions because the two triangles are similar. Yeah, right? Okay, wait, it's almost time.
One.
I wanted to uh, nothing. Like it's almost time at this point. I wanted to discuss another question, like, but oof. Okay, so we have this. We have fx is equal to bf by ce. So here we have this point as well. It should be pretty easy to calculate this. I'll just leave that as stuff to do. And it's like easy to calculate all of these points. So you have to get your hands dirty on this. And yeah, that basically concludes the problem. I also wanted to do another problem, uh, but it's time at this point. I don't think anyone like wants to extend the session, right? Like there are only a few people here. Anyways, yeah, thank you for like attending the class. Like also, if it's okay, can you guys like wait? I should stop the recording. Uh, pause. Stop share.